God. There we go. I just turned it back
Okay,
on.
great. Thank you. Because all I can see now is this big slide. That's all I can see. All right. So, Michael, you want to welcome everyone?
Yes, I'll
Thank you.
So welcome to the inaugural Careers in Technology Fall Series 2024. We originally started this as a summer-only series, and we were asked to expand it to spring, summer, and fall. So without further ado, I will pass the baton over to Kit, who will introduce our speaker for tonight's kickoff meeting for Fall Series 2024.
Thank you so much, Michael. Thank you for creating this fabulous series and sharing it with other regions, and hopefully other people all around the world will be able to benefit from your guidance and this project. Li Feng, you want to say hello?
Hello, everyone. So nice to meet you, everyone. And I'm currently a assistant professor from Lehigh University, and I'm served as the IEEE the Computer Society chapter chair at the Lehigh Valley sections. Thank you, everyone, for joining this event tonight.
Thank you. And Raj?
Hi, this is Rajesh Murthy from the Montreal chapter, and thank you all for joining the session today.
Thank you so much for your patience with me learning how to use the slideshow. And now I'd like to introduce you to this session, which is Careers in Technology with Professor Dr. Victor B. Lawrence from Stevens Institute of Technology, previously from Bell Labs, and my boss. These are the sessions that will be coming up soon. Hopefully you folks will join each one of the sessions, subscribe to each of the sessions, and get individuals to join the community, which Michael will tell us about in the future. So to register for upcoming events, this will be made available to you now and later on. Victor Lawrence retired from Bell Labs as Vice President, Advanced Communication Technology, AT&T Lucents. Later joined the Stevens Institute of Technologies, where he is Senior Research Scientist, Director of Intelligent Network Systems, and former Associate Dean and Batchelder Professor in the Department of Electrical and Computer Engineering. Dr. Lawrence was inducted into the National Inventors Hall of Fame in 2016. You know, again, we have this thing here. Okay, I'll move it over there. Great. Okay. He is a member of the National Academy of Engineering, a fellow of IEEE, fellow of AT&T Bell Labs, and charter fellow of the National Academy of Inventors. He is the 2023 recipient of the R&D Council of New Jersey Science and Technology Medal. While at Bell Labs, Victor Lawrence led the development of technologies for worldwide communication networks and managed an R&D staff of over 500 scientists, engineers, and a budget of about $100 million annually. During his career, his personal research activities provided major contributions to gigabit photonic and wireless networking, signal processing, modem technology, digital techniques, ATM and IP switching and protocols, HDTV, DSL, speech and audio coding, among other areas. Dr. Lawrence holds a BSc, DIC, and PhD from Imperial College London University. He has served as chairman of the IEEE Awards Board and editor-in-chief of the IEEE Transactions on Communications. During his career, his personal research activities provided major contributions to gigabit photonic and wireless networking, signal processing, modem technology, digital techniques, ATM and IP switching and protocols, HDTV, DSL, and speech and audio coding, among other areas. Dr. Lawrence's innovations in the fields of digital signal processing led to the transition from analog to digital networks and to the development of technologies for early access to the internet and worldwide data communications, including the first chipsets used in voice terminals for secure communications worldwide, and the first PCMCIA modules for wireless data modems. The work conducted by his teams impacted not only entertainment video, but also broadcast satellite radio. They built the first studio encoder and receiver chip set for the Sirius radio satellite system. Please see also the Light Millennium website, which is part of the United Nations, and Victor's involvement is very significant in these activities of humanitarian needs around the globe. Victor Lawrence has been a key proponent of R&D globalization, At Bell Labs, he directly supported systems engineering developments and practices in Malaysia, New Zealand, China, Brazil, and other countries. He was a member of South African President Mbeki's International Advisory Group on ICT, chairman of the Broadband Advisory Committee to the South African government, and a director of the board of Telkom South Africa. He championed bringing fiber optic connectivity to Africa. Beginning in 1996, Lawrence lectured for several years at the Dwight D. Eisenhower School for National Security and Resource Strategy, formerly the Industrial College of the Armed Forces. He also served as a visiting professor at the University of Pennsylvania, Rutgers University, Princeton University, Columbia University, and the University of California, Berkeley. Since 2015, Lawrence has made significant contributions to the development of STEM education for high school and middle school students in New Jersey. He currently serves as a trustee of the New Jersey Center for Teaching and Learning. These are some of the awards that Dr. Lawrence has been awarded, and some of the most recent ones include the National Inventors Hall of Fame, 2023 Honorary Doctorate of Dominican University, and he's the 2023 recipient of R&D Council of New Jersey Science and Technology Medal. So some of the documents that you may find information about Dr. Lawrence include the United States Patent and Trademark Office report to Congress, the Success Act from October 2029, which features his patents and achievements in signal processing and telecommunications. You may recognize some of our other friends from Bell Labs on this page and other people that we know from the industry and around town. This is an excellent document. People should pick it up, look at it. We'll learn a lot about what has been achieved and what's yet to aim for, what we should strive for. One of the other awards that Victor Lawrence has received in the Grand Alliance, which was a consortium created in 1993 at the behest of the Federal Communication Commission, they developed the American Digital Television, which is HD TV specification. Obviously, that consisted of AT&T Corporation, General Instruments, Massachusetts Institute of Technologies, Philips Consumer Electronics, David Sarnoff Research Center, Thomson's Consumer Electronics, and Zenith Electronics Corporation. This won the Emmy Award. So moving from analog to digital TV to HD TV, Victor Lawrence was part of the consortium that won the Emmy Award for this technology achievement. So as we all know, our background is at Bell Labs. Many of us on this call are from Bell Labs, have our roots in Bell Labs, and Victor Lawrence, of course, has his roots in Bell Labs. And the IEEE has spent a lot of time. As you can see, there's a meeting pictured here from 50 years ago where IEEE was holding a meeting, and members of the Bell Labs staff are conducting technical talks to members of IEEE, sharing scientific and technical information with people from industry, government, and educational institutions, regularly exchanging ideas. So coming up very soon, one of the things that Victor Lawrence is a champion of is recognizing the achievements of others. One very important achievement will be recognized soon in the IEEE milestone for the Nucleodyne Circuit 1922 that will be celebrated on the 19th of October 2024 from 12 noon to 2 p.m. at Stevens Institute of Technologies. This milestone represents the achievement of Professor Dr. Hazeltine, who embodies this important message that we have of advancing technology, specifically sustainable technology that benefits humanity. What this gentleman did was to take something that was a monopoly. The radio industry was a monopoly, very expensive. Many people couldn't afford radio. He turned this into a device which he licensed to many, many people. This is the Nucleodyne Circuit that took radio communication from only 10 million people in North America to 60 million people in North America, which was a significant achievement in only 3 years. It changed radio into a popular form of mass communication where people could participate, receive information, culture, transforming opportunities for everyone. People could learn a similar language. People could learn about music, things that happened recently, to become active members of a democratic society. And this is the very best example of how technology advancement can be used to devote purposeful humanitarian missions. And Victor Lawrence has been an advocate for this through his entire career and still today. So
So
I
I
just
just
like
want to say this, that Stan is the successor of Louis Heseltine, because he was department head of electrical engineering, and Stan was also department head of electrical engineering. Is that right, Stan?
Stan, are you
is
there?
muted. Stan
Ah,
is muted, I guess.
Dan, can you unmute and make can you say something at the risk of not knowing how to get back into slideshow mode.
Don't do that then.
Let me unmute Stan. Can somebody unmute Stan? Uh-oh.
So maybe he will say it at the end.
Uh-oh. I
But
lost the
he is the
window.
successor. He is the successor of
Oh, there
Louis.
we go. Okay.
Yeah, he's unmuted now, Kit.
Oh, he's unmuted. Stan, can you say something for us?
Okay, what do you want me to say? I know Victor asked me something, but I couldn't hear it.
Ah,
Oh, what I said was that you are the successor of Alan Louis Hazeltine, because he was the department head of the electrical engineering
Complete.
department at Stevens.
Yes.
And so you come after him.
Oh, after several in between.
Mhm. Yeah, but you are the successor. Yeah, one of
so
the
we
successors.
just love to honor the legacy of somebody so admirable as Professor Hazeltine. He really changed the world, and you know, these things are evident in our everyday life. So I hope you'll join us in this celebration that's coming up. Now I have to find my slides again. Oh no, where
The
are they?
slides are on. They are on.
Oh, they are?
So,
Oh, okay.
Stan, will you be able to come on October 19th?
I'll try. That's what
Okay.
day of the week is that?
It's a Saturday,
Saturday?
October 19th. Yes,
Okay. It's going to be at Stevens?
at Stevens.
Okay.
I will make sure they send you an invitation, Stan.
I probably already have one, but
Yeah, I think so.
yeah,
But I'll make sure. Yeah.
sure.
No, I really can't see these slides anymore. Oh, there they are. Okay, good. Can you see the slides? Can everyone see the slides?
Yeah.
Good.
Yes,
Okay,
we do, Kit.
excellent. So now I can't seem to get them to advance.
Yeah.
Ah, wonderful. Thank you. So another one, let's do another one. Wait. Okay. So this is the outline for Professor Lawrence's talk. And now without any further ado, I think I don't need any other slides there. Great. We will move to welcome Professor Victor Lawrence.
Thank you, Kit, and thank you to all of you for coming tonight. Yeah, Kit asked me to talk about my life and the things that I have done. And so I was thinking about that, and I know why I got involved in electrical engineering and why I decided to do a degree and a study in electrical engineering. One day in 1962, when I was in Ghana, me and my classmates in high school just before, were sitting under a tree, and we only had a shortwave radio. And we heard the speech of President Kennedy. And he said that we'll choose to go to the moon. And so we all wondered, because you're sitting under the tree and you're looking up and you see the moon far away and you're asking yourself, how can this be possible? So my classmates and I started thinking about this and researching and going in to find out what has been done. And we found out that earlier, about 6 months earlier, Senator John Glenn, please advance the slide. Senator John Glenn he was that astronaut who was the first American to orbit the Earth. And so this stimulated our interest, and mine in particular, in engineering. And so I left Ghana with a scholarship to United Kingdom, where I did my bachelor's, master's, and the PhD. But when I finished my bachelor's and started the master's, I went to the professor, the head of department, and I expressed to him my desire to be able to do a master's and a PhD. And he asked me, what do you want to do? What ideas do you have? And at that time, I had some crazy ideas about doing something in 3 dimensions, or 3 dimensions, I was saying. So he looked at me carefully and he said that he said, Victor, you know, why don't you start with 1 or 2 dimensions? And he said they had invented that Bell Labs had invented the transistor, and he had bought one for the lab. And so he asked me to go and learn about this transistor and see what I can get out of it. And that was what spurred my interest into the digital signal processing, because what happened was that the transistors were zeros or ones instead of analog signals. Please advance the slide. And so, as you can see, before the invention of the transistor, the type of things that were used in the network and by our engineers were vacuum tubes, and that's the one on the far left, if you are looking at the screen. And of course, the transistor was invented in 1947, but it took a long time for it to be adapted into the communications network. And I'm talking about 1968, 69, when I had this encounter with my professor that told me to go into the lab and start learning about the transistor, connecting things to it, and then observing the ones or the zeros that come out of it. Next slide, please.
I'm trying.
Mhm.
It doesn't want to go. There we go.
Okay. And these
There you
are various generations of the transistor being invented in 1947. And as you can see now, I mean, these transistors, billions of transistors are put on a chip the size of your fingernail. So you can see the 3 inventors, and they got a Nobel Prize: John Bradeen, Breton, and Shockley. And this was in a lab in Murray Hill. And that really changed the world. Next slide, please. Okay, so this is what happened to me. Before I learned about this, I mean, people were using the vacuum tube, and they were using analog circuits that you can see on your left, the capacitors, resistors, and coils. And on the right is the digital filter with the transistor above it. So you can see the digital filter was nothing more than a multiplier, an adder, and delay elements. And this was the basis of the digital filter. And so I did my thesis based upon digital filters and the design of digital filters for the communications network. And I was lucky enough for Bell Labs, AT&T, to notice my work. And they came over to England, Imperial College, and they recruited me to come over to the United States and work at Bell Laboratories. Next slide, please. The next slide, please. This is just an analog filter. Okay. So when I came from England to the US, the first assignment I was given was, okay, so you have been doing digital filtering, and you've been doing it analytically and simulations. Why don't you build it for us? That's what AT&T asked me, Bell Labs asked me. So I got to work, and I started building. I said I was building a filter. And you know, my filter became an oscillator. And that was a big flop. But anyway, I had to go back and find out why my filter is not a filter, but an oscillator. And I found out that it was mainly due to the effects, because this is all digital. What had to happen is that, and of course, you also don't have to have infinite precision. And therefore, I had to quantize the words, and the processing was all done in finite precision arithmetic. And when you have finite precision arithmetic in digital filters, the quantization effects can cause a problem. And I found out that my quantization effects were the things that made my filter become an oscillator. And there's something I discovered also called limit cycles. The output of the filter, if you don't take care, will keep oscillating, and we called it a limit cycles. And so I had to correct this limit cycle, and I was able to do so. And so I was able to get a perfect filter. But I also learned how to do a perfect oscillator, because my failure turned into a success of designing very good oscillators. Next slide, please. Next one, yes. Okay, so then the labs asked me to look at the design of modems using digital filters. So you can see these are modems that were initial modems that we had. Next slide, please. And this was a block diagram of a modem. Maybe the next slide will be a better one. Yes. Okay. So you can see this block diagram of a modem. It consists of nothing more than digital filters, oscillators, delay lines, and digital circuits. So one of the first things that we did was to develop modems at very high speeds using digital signal processing. And the first time we did this was also a failure, because what happened was that we disabled the echo cancelers in the network. The echo cancelers are used for the speech processing, and we disabled them, and that was a big failure. And so we had to go and find out what the cause of this was. And we found out that we only needed to put a single 2100 hertz tone inside the spectrum of the data. Next slide, please. So we worked on this, and so we moved data from 1200 bits per second all the way to 14,400 bits per second. And we went on to standardize this. So this was really the beginnings of the early access to the internet. And we had these standardizations called the CCIT standards, V22 base, going all the way to V90, which increased the speeds from 12 to about 34, 1200, that's 1.2, to about 34,000 bits per second. But these are low speeds. But in those days, in the 70s and early 80s, this was just a revolution. That's how you could transmit such higher bits. And therefore, it made possible to do many things in the facsimile. You will see it later on in secure voice. Next slide, please. So I'm talking about the early access. So one of the first experiments I did was to transmit data over the transatlantic cables from Bell Labs to British Telecom. And this was very successful at bits up to 9600 bits per second. And then we also did another from the labs, Bell Labs, New Jersey to Japan. So we did the first full duplex. This was full duplex, moving data in both directions over the network. and this justified the CCIT standards. We presented this to the worldwide ITU, and they standardized on this. And so we used modems for a long time before and now that we don't talk about modems, we talk about DSLs and wireless. Next. So one of the things that I capitalized on was because I started with a digital filter, and it's based upon multipliers, adders, and delay elements. It was so easy to put that into a chip. So the first thing we did was we took a whole 2400, 9600 bits per second a modem, and we made it into a switch capacitor modem, and then later on made it into a single chip modem. So we had the single chip modem, which we called the data pump. And this made it possible for us to use it in many applications. So let's talk about the first application, Kit, please. Yeah, the first application was in the secure voice terminal that we built. And you know, the secure voice terminal is nothing more than an A to D converter, the speech signals, you digitize it, and then you have a speech coder, and then you have to encrypt it. Because it's digital, you can encrypt it. And then once you encrypt it into the ones or zeros, you can put that through a modem. And that was the modems that we were building, and of course, the digital filtering and things that are in for the speech coders. So we did this first secure voice terminal, which was very, very successful. It was used in 1989 by the President of the United States, and also by the Joint Chiefs of Staff and the Secretary of Defense, and it was successfully used during the first Gulf War. So now we had the secure voice terminals, but it includes nothing more than the modem that initially we designed. And it was incorporated, it was in the chip incorporated in these terminals. Okay, so let's go to the next slide. Also another application. Yeah, this is another application of digital filtering into text to speech and other things. The next slide. So one of the things we also did was we applied this digital signal processing, the digital modems and the filters and so forth in applications for digital radio. So one of the things we did was, before then, radio was all analog. And so we changed that into a digital radio. And then we also did the satellite, the series radio satellite. So now we could do this, and the series radio satellite, what we did in the ratings for the series radio, in fact, we did it, the whole thing for Sirius XM. The designs were based in Bell Laboratories. And so we did a transmitter circuitry, we did the receiver, and we did all the systems engineering associated. So now whenever you are using the series radio, you know that these are the genesis of things that happened that within my lab in the Bell Laboratories. I had my whole team working on this. Then not only did we worry about speech, but we started looking about video as well. And we went on to move video from analog to digital. And you know, all that it is that the video signal is now digitized, and we use the modem, and therefore we then transmit this digitally over the network. And this led to digital video, and then eventually to HD TV. So HD TV is now digital, high definition TV. Okay, so, you know, as I was looking back and seeing what was happening, I looked at the various ASICs that we used, the chips that we used. You know, we started with the microprocessor that was invented at Intel, but it was the genesis is the microprocessor is nothing more than the transistors. So many transistors make a microprocessor. And because there was the microprocessors were very good at doing additions and so forth. But then for the processing, for multiplications and so forth, of course, we had to use what we call the digital signal processors. And now, you know, we found out that it progressed on to graphic processing unit, GPUs. And a lot of the things that you see are graphic processing units. But the future would be AI processors, as you can see. So one of the things that I know I did the first experiments to prove that data can be transmitted at speeds of 9600 bits per second over the transatlantic cable, over the transatlantic network, and also over the Pacific networks. So one of the things I started looking at is, okay, so the network, then the transatlantic network and Pacific network is not only satellites, but it was submarine cables. And so I turned my attention to submarine cables. I found out that there were a lot of cables from Europe to America, from Europe to Asia. But at the continent of Africa alone, there was very little or none of submarine cables in the, just before the 1990s. So AT&T asked me to turn my attention to see how we can put submarine cables also around Africa. So this is what you can see. The red shows this. And when I started looking at this, yeah, this is fine.
Okay.
I found out it was very interesting. What was the communication used before we put submarine cables around Africa? You know, there are two towns, for instance, I don't know whether you can see them, but Accra in Ghana and Lome in Togo, they are only about 130 miles apart between the two capitals. But if you want to make a communication, if you want to speak or make a communication between the two capitals, you had to go via satellite. For Accra, you have to go to London. From London, you switch to Paris, and then from Paris to Lome. And it's mainly because those countries, Ghana was a British colony, so most of the communication over satellite was going to London. And Lome was a French territory, and so most of the communication was going from Lome to Paris. And so you had to do the switching there. And so you find that it's very interesting. You are talking about, instead of 130 miles, you are talking about 10, maybe 7,000 miles of communication. So I started looking at this, and that was the concept of the submarine cable around Africa. We called it AT&T, we called it Africa One. So the next link, next slide. So you can see one of the things that is interesting is this is the worldwide. So today, worldwide communication over on the ocean, inside the ocean, over satellite, over fiber optic links, is very dense. You could see now Africa has got a few cables around it. And then, of course, there's a lot of traffic from North America to Europe. You can see how thick that part is. And then, of course, the rest of the world in Asia and so forth. So one of the things I did was to do the first systems engineering studies and the designs that are being used today for submarine cables around the world. So let me say a few things about submarine cables as well. The next one, slide, please. You know, one thing is that these things are costly. So submarine cables, when you do that, you have to have a consortium of companies all contributing to it, a consortium of the telephone companies. And now even the consortium includes the companies like Google, Facebook, etc. Because they are transmitting a lot of data around the world. So they have been also building submarine cables, but it's based on the original designs that we did at Bell Laboratories. So every cable is a consortium, and there's an arrangement that so many telephone companies own that cable. It's not only owned by one person, by one company, because of the cost and because of the maintenance of that. But you know, there are always difficulties with submarine cables. You know, in satellites, it's easy because there are not too many difficulties because nobody can tamper with it. But with the submarine cables, they are on the ocean floor about, I think it's only about 7 kilometers, the ocean floor is. And therefore you could have many difficulties. There are many accidents that happen, and so therefore you have to harden the cable, because the fiber cable is just the size of the thickness of your hair, and that can never survive under the ocean. So you really have to harden, put things around the fiber. Okay, let's see the next one. The next slide. Of course, one of the difficulties as well is that fishing boats can cut the cables, and sharks and other things can also try and bite into the cables. So you really have to harden it. And there may be some slides that you can see later on. So this is a problem of it. Then the next one, I can just...
So here we have seismic activity linked to the undersea cable breaks.
Yeah, I think somebody was sending a message. I guess you are not hearing me properly, is it? Okay. Anyway, yeah, there was a seismic activity also. Go to the next slide. Maybe it may show it much better. And then, of course, you may also have heard that the recent thing about the Red Sea, the cable around in the Middle East was cut also, and that prevented a lot of difficulties. So you can have terrorists cutting these cables. You know, it's difficult for the satellite because they can't climb there. I mean, if they have to go with another satellite or something. But it's very easy to cut these submarine cables. But the submarine cables have got a lot of capacity in trillions. For instance, on one single fiber, you can have 1 trillion bits per second on a fiber. That means that 1 billion conversations can go on one fiber. So you can put so many, and the fiber bundles are in the bundles of about 16 fiber pairs or 24 fiber pairs. And so you can find out the amount of traffic that you can carry. And I said you can have 1 billion speech conversations, but then of course you also have to transmit video, which of course it's much more bits are needed for video. Okay, so this talks about some of the things that Bell Labs did in the submarine cable for Africa. These are some things about the submarine cables. You can see the vessels as they lay the cables at the seabed. It's a very interesting and challenging thing. And here you can see the cable. You can see the fiber is the one in the middle, if you look at the cable on the right, then you can see that it's bundled and made very thick before you can, and you do it in such a way that sharks and fishes cannot bite into it. And these are, you can see how big these fiber cables can be. This is me in the AT&T labs with some kids from some again primary schools and middle schools that visited the AT&T. One of the things that also you need is, because the distances are long, you need repeaters. And so at the top you can find a repeater, how a repeater looks like. So you can see my life and my history. I failed many times. My first attempt to build a digital filter straight from university, AT&T asked me, put in a lot of money to do that. My filter became an oscillator, but the learning was that I found out the best way to build an oscillator. Oscillators are necessary because they are things that we use in touch tones and so forth. An oscillator is just a tone. And of course, so I learned how to build a nice, from my failure, I was able to learn how to design a filter, a digital filter, a very stable one. And then, of course, when I started the modem work, trying to put the filters into modems and into the network and transatlantic cables, I also disabled the network echo cancelers, and that caused some problems as well. Now, believe me, the work on high definition TV was very difficult as well. It was spent sleepless nights trying it out because it was the first time. Every time you have something for the first time, it's always a problem. But my thing is that you should never let a disappointment overcome your hopes and dreams and aspirations for the future. There will be many mistakes that you make along. So this is part of my life and part of my career. And of course, I am now heavily interested in helping doing STEM education. And you can see me with some of the students. So thank you.
Thank you so much, Professor Lawrence. I hope everyone has enjoyed meeting Professor Lawrence. There's some applause here, and I hope that we have enough questions for people. Thank you, everybody. Does someone want to volunteer for the first question? Hi, Jeremy. How are you? Hi, Nate. Hi, Stan. I saw some of the applause here. It's very nice. Al, thanks for joining us. Anybody
Okay.
want to ask a yes?
I'll start with the first question.
Sure. Excellent.
Thank you, Dr. Lawrence. That was very motivational. What or how did you handle failures?
Yes, they are big disappointments, but the organization, Bell Laboratories, was a very unique organization, and they were very much aware that you try and fail before you become successful. And so they were lenient in many ways. They didn't fire me, for instance, when I spent so much money on building a digital filter, it became an oscillator. They rather encouraged me to find out what the problems were. And how do I handle it? I handle it by trying to tell myself that I can find a way around it. I know that. And the people that I had a big organization there later on in life at Bell Labs. I had about 500 engineers and scientists that were working for me or in my organization. And then, in fact, the labs gave us $100 million every year to do research. And so it was a unique thing. But of course, this whole thing started falling apart after divestiture, intravestiture, and antitrust and so forth. But anyway, you could see how you could have they invented the transistor. You could see how they invented the laser. You could see how they did the original work on satellites, and even Unix, C++, and so forth. So it is really the environment that really helps. And I got into this environment and I learned through it. And therefore, I also adopted this, that I have to think about people that are working with me and for me first before I think about myself.
Thank you. That's very inspiring. Does anyone else have a question for Dr. Lawrence?
I have a question.
Yes.
George.
Yes.
Hi there.
George Aguilera here. Out of, I think you said maybe 47 dimensions is what you were faced with originally when the professor gave you advice as to where to go in the
Yes.
lab.
Yes.
If you were to pick 3 today, what are the dimensions that you would select going
Oh,
forward?
well, you know, today, I mean, technology has improved. I mean, the digital signal processing and computers are fast and so forth. So when I was telling him about 3 dimensions, this was in 1968. So he knew that I was raw and I didn't know what I was really talking about, but I had ambitions because I had said to myself, oh, let me do something in 3 dimensions or 4 dimensions or something like that. So today now people are doing great things in many, many, many dimensions. In fact, even when I was in Bell Labs around maybe just before the year 2000, they had 6D mouse, you know, that they were using to navigate things. And now so now I guess I would say that the sky is the limit. Computation power
Literally.
is so great.
Literally have the satellites to think about, right? Deep space. It's really cool now, right?
Yeah, the sky is the limit. I think technology has improved, but you can imagine what was in 1968. And of course, I could go back into the 1940s when they invented the transistor. I mean, they didn't, nobody knew that this was the effect it was going to have. But one thing is that industrial labs have to be very tolerant. The universities have also should be encouraging new ideas, new things all the time.
Do you think it is like helpful for people in your situation or any of us to get involved with mentoring younger people or even people
Oh,
who are our peers and so forth?
yes, very, very important. The mentoring is very, very important indeed. And you know, mentoring, sometimes you learn not only from your mentee or the things, you learn also from the mentee, you know, not only the mentor always being right. Some of the younger ones have got brilliant ideas, and those have to be encouraged. So the mentor and the mentee have to exchange ideas.
Is this sort of like a path for lifelong learning if you get involved?
Yes,
Yeah.
yes, it's part for lifelong learning. It is indeed. But you can see, I'm just looking back and saying to myself, in 1968, could I have imagined any of these things? But it was the invention of the transistor in 47, and it took me 20 years before I got, well, what I meant was that it took 20 years for us to see the transistor in a form in a lab, in a university lab that we can use. So things take time, but I guess these days things, innovations come much quicker than they used to.
How long do you think it will take for the world failed to realize some level of connecting the unconnected. What do you think we can do to help bring that aspect of sustainable development goals into reality?
Yeah, I think that has to be worked on now. And in fact, in the worldwide, in fact, in the US, for instance, there are many places where they are, it's very difficult for broadband services. And I believe that Congress and other places, they have a program called the BEAD program, Broadband Equity Accessible Deployment Program. And that's going on. And I think that within the next 5 years, you will find that maybe there's every home in the United States would have broadband connectivity. What I mean by broadband is 100 megabits per second both ways, or maybe 100 megabits per second downlink and maybe 20, 50 uplink. But this is going on, and it's also going on in China, it's also going on in Asia, and believe it or not, very interesting indeed. Africa is leapfrogging a lot of the things because it doesn't have any legacy things that it's building upon. So most of the new things in wireless are happening there. They are trying it out there. And in
So we
fact,
have a question from Christine. Would you like to unmute and ask the question? Or would you like me to read it for you? Christine? Okay, I'll read the question. Thank you for the work you've done and for sharing this with us. I have a question. How have you or do you recommend keeping up with the research, especially in fields like AI that are changing very rapidly?
well, it is important to keep abreast. I have this vision that you have to continue to invent, and also you have to ask yourself the question, fundamental questions like why not? You see things as they are, and you ask the question, why not? Can't it be done in a different way? And then, of course, when you talk about AI today, many people are afraid about AI because they think it can have adverse effects and so forth. But, whatever has been invented can never, never be uninvented. And we have to learn the best ways of using it. And therefore, I see that the pace of innovation is much, much higher. In fact, I have a chart that I used to use at Bell Laboratories. In the first 1,000 years of creation, the only means of people communicating was by the pencil, eraser, and paper for the first 1,000 years. But then the next 100 years was much faster. The next 10 years, then the next 10 years after that was much faster. So you really have to keep abreast with technology and try new things, adapt, be one of the technology leading adapters of technology. So that's how I see it. But AI is coming and AI is here, and we have to learn how to use it. People worry that it's going to affect other jobs and so forth. But I think that it will also open new areas of opportunity. But I come to this conclusion every time that there is nothing wrong with science or technology. What is wrong in today's world is the nature of the human being. The human being has increased his power over nature, but not over himself, him or herself. And that's why we have a lot of problems.
So there is a question here about the power consumption of AI and how it compares with perhaps previous innovations like the transistor, which did not have a similar impact on power consumption. So this, seems like a really big challenge for us, and it's something that we can aspire to resolve as engineers, taking on sustainable and resilient technology as an issue. Do you have a few comments
Yeah,
about?
so you do this in both ways. You try your very best to find the best algorithms that you can, the algorithms that are very efficient, that will consume less power. But at the same time, you also have to find ways in which you can have cheap energy for the processing. So you go two ways. You finding cheap energy at the same time as improving your algorithms in such a way that they can consume less power.
And Stan has his hand raised. Stan, can you? Yeah.
Yeah, as far as artificial intelligence goes back many, many, many years, I still think it's a misnomer. The computer doesn't have the intelligence. It's the person who develops the algorithms and writes the code who has the intelligence. Okay, the computer just implements it. And
Yeah. It's like the ADA test. Do you remember the ADA test? Yeah.
In fact, years ago, Stevens had a program in artificial intelligence, probably in the 80s, I would guess. Okay. And at that time, I was invited to give a talk at DARPA. And it was kind of interesting because people from Brooklyn Poly were there, and they had what they called an expert system. The conclusion I gave in my talk was basically, if you wanted to develop an expert system, hire an expert.
That's right.
Nothing replaces the human mind yet.
Yes. The difference is, Stan, is that because you are able to do many, many, many more computations, you are able to get an answer or an understanding of something.
Well, it's not only that. It's the fact that you have an enormous database of information you can rely on. I remember doing some reliability studies and risk analysis and things of this sort, where, for example, there were some expert systems done for the years ago, back in the, when did I use them last? Probably in the 20 years ago. Okay, that would allow you to, for example, to make decisions. Say, I want to buy a computer. Okay, what are the criteria for buying a computer? Speed, power consumption, cost, all of these things. And what you do basically is you insert weights. Okay, where do weights come from? They come from your mind. How important are each of these things? Well, now you have an enormous base of information out there that you can rely on to help make those decisions. And with the high-speed computing capability, and I've been arguing, I've seen this argument go on for years and years, particularly with the Department of Defense, is that they justify new programs because, well, we have more computing power, we have better processors, we have cheaper processors, we have more reliable processors, we have more memory. Memory's cheap, memory's not cheap, but in the sense of reliability and things of that sort. But these are things that you have to worry about. And now you have computing capability where you can make decisions based on more parameters and more information that's available, somewhere out in the ether.
Yes, Stan said it.
Sorry, Victor, Stan, just to extend what you were saying. In terms of intelligence, I've read that intelligence is defined in multiple ways. But when we consider just computability, what are your thoughts on how we can utilize computability to create a more energy efficient pattern matching engine so the systems don't hallucinate?
Well, I'm not quite sure what you mean by efficiency. Efficiency is, it can be done, efficiency of code, efficiency in power, efficiency um, in various aspects. Okay, I'm not sure right now where we're going with respect to that. Maybe quantum computing is a possible development. Okay, that we don't really know yet. We can kind of predict what's happening. We see some things happening in the quantum computing area, but is this going to be the future? Don't know yet.
Thank you.
Yeah, when you mention hallucinate, yeah, I know what you are what you're saying, and you know, sometimes systems can keep going on and become unstable, and they can keep going in the wrong direction. So I know that sometimes things like that can happen. And
well, you know, the more complicated things get, and the more computing capability you have, you know, if you just look at reliability, the probability of errors occurring, it's more and more, you know, probability gets higher and higher as you're going to get errors.
that's right.
You know, and when you develop code for AI systems, it becomes more difficult to look at the reliability aspect of it, to look at all the possible combinations of decisions that are possible and which ones, for example, won't cause the system to blow up. So it's, you know, there are advantages and disadvantages of high-speed computing.
Yes. And you know, the human capability is enhanced with machine learning and things, you know, or even smelling. In fact, there are microphones or hearing. There are microphones that can pick up sound million times better than a human being.
Sure.
And then also the same with yeah, smell and chemicals, much more than a human being can. And in fact, even dogs sometimes can smell much better, smell much better than human beings. And machines are now much more capable.
Victor, do you remember our colleague Dan Lee, who had been working on, was it the bloodhound to smell things, artificial intelligence? Yes, yeah. There were other people working on biologically inspired intelligence for many years at Bell Labs. And some of these things, when in Victor's slides, if you look carefully, you'll see many of these things represented in the slides that weren't deeply covered in today's talk, but certainly there's plenty of opportunity for us to revisit many of these ideas in additional sessions in the future. Would people be interested in such things?
For sure.
I know I would be. Yes, excellent. Okay, and I noticed Dr. Iwama is with us tonight as well. One of the slides pointed out one of the projects that he was well known for, the Telstar.
The satellite,
Yes. So there are people on this call, on this meeting, who I think would love to rejoin and have an additional conversation in this related topic. Am I right? Excellent. This is very cool. Bruce, I wondered if you had a moment. Can you share with us some of your thoughts? Did I call upon you? Are you there, Bruce? Aha, not okay.
I see Bruce, but
yes,
I don't
he
think
may not
his,
be. He may be traveling or something. You know,
Yes.
listening does anyone else have a contribution to the discussion that they would like to bring? Yeah, so there's a question in here about sort of the economic models, et cetera, the direction. I'm guessing the direction that the AI and other average consumers may be affected by some of this new technology that we're sort of raising here, and how, as Victor pointed out, 1,000 years of progress, the pencil and the paper, 100 years of progress, tremendous differences in communication. The next 10 years may bring lightning changes, lightning speed changes in certain domains that affect people's everyday life. We often talk about how STEM isn't just a choice for the top people in school anymore. It's now everybody's job, has some STEM aspect to it. So in thinking about that, Professor Lawrence, do you have a point of view, a perspective about how we can help people in our community to be to embrace STEM, to make it part of their vocabulary, to, like you said, not to be shy, to reinvent yourself, not to be shy about making a mistake and just moving forward? Are there some words that you may have that may help us with that part of this
No,
project?
yeah, STEM education is very important because you have to keep abreast
Thank you.
with what you are seeing, what is happening.
Mhm.
And then also one of the things that I'm very much interested in is helping the blind of something be able to see better, helping the deaf to be able to hear. There are all these things that science and technology can help. I
And
mean,
it's really nice to have the vision of those goals and to be able to become more aware of STEM, because we turn to technology to solve many of our problems. But to have the ability to not be afraid of technology, not to be afraid of learning more all the time, every day that we wake up, we should be able to learn something more, right?
yes.
And yes, I think we have great examples here on this call. And it would be really, really wonderful if that's a message we can share with the people around us. Right, Victor?
Yes. Yes.
Are we getting too or over reliant on technology?
I think technology is our vocabulary of today and the future. And until, like Victor was saying, you can't uninvent something, right?
Yeah. You must find the
So,
best ways of using it.
right.
So are the humans really capable of figuring that one out? We seem to be going on the wrong direction every time something innovative comes along.
Yes, because they are bad characters that will always take advantage of that, whether the cybersecurity that you see happening today and people calling you every day to tell you something, and if you follow them, they may get your password, or there are so many things, and of course, although technology can be used in medicine and help, there are also the side effects of it as well.
Right. And this thing about having a positive ethical compass or moral compass. This is something that a professional society like IEEE can help us to, become more aware of, and to share in this room, in our room, where we share these ideas about how to advance technology to benefit humanity, which is really the mission of IEEE. And so over time, over the past 100 years or so, how long has IEEE been around, Bruce? Do you remember? I mean, in all of its various forms. When was it founded? Do we remember? Does anyone know? A long time, right? And since Edison and Bell and all of those people got together. And so I think this organization serves a purpose to help us keep grounded in these ethics and values. Stan, you have something to say about that?
No, it originated with the IRE,
Mhm.
AIEE. Okay, and now that probably goes back to
1884?
50s, maybe.
1884, yeah. I mean, so we all know these things. They just don't always roll off our tongue. And pretty much every year someone's having an anniversary. It's the 50th year of that, it's the 75th year of this society, and so on and so forth. But the fact is, this is a 450,000 member society, global society, right? And with the mission of advancing technology for humanity. So if we keep gathering in this room and sharing these thoughts, not only will the technology be more beneficial to humanity, but we'll keep our compass, hopefully. This is, you know, we can only hope for that. Right, Victor?
Yes.
Let me just say thank you so much for joining us today. If there are any other comments, Christine has another question. Christine wants to know, humans are overpowering nature and not having power over themselves. There was a
Yes.
comment that you made earlier. Do you remember
Yeah,
the
I said
comment?
that.
Yeah.
I said that, yeah, we humans have, yeah, been able to have the power over nature, but not over ourselves. I mean, we can go to the moon, we can do this, we can do that, but ourselves, we don't have the power to control ourselves and be good actors and not bad actors.
So Dr. Geeta Sandeep Nadella says, must leave, but want to say thank you so much for speaking with us today. There have been a lot of comments, positive comments. Steve, are you still with us? Steve Wilkowski, are you still with us? Steve? Nope. Oh, yes, you are. There you are. Okay. Why don't you say hello? Are you there? Yes. Excellent.
Yeah, I just wanted, yeah, if I can try to unmute. Yeah, I always have network problems. I
Sorry.
won't say who my internet provider is, because that wouldn't be fair. It's great to see you, Dr. August, and Professor Lawrence. Always good
Pleasure.
to see you.
Pleasure to see you, Steve.
And
Looking forward
thank you to you, Stephen.
to
You always
that event
in Stevens, yes.
Yeah.
And you always come out and help us with our humanitarian projects and our mentoring and all these other activities. I'm very, very grateful to you and your wife, who always participates in as many things as she can. Thank you very much. There are a lot of people on this call who have been out and about with our mentoring and volunteering and various activities. So I just want to say thank you to everyone. And Tom or anyone else, you want to say anything? Tom? Are you there?
I can't, just always glad to have some interactions with Victor Lawrence. He was a great gentleman. I remember when he was back at Bell Labs. I remember a lot of the work on the digital television standards in the 1990s. So yeah, always good to hear from Victor, and look forward to the next time we get together face to face in Middletown.
Excellent.
you.
And
Thank
Bruce is what has
Hey.
come up. Hi.
Hi,
Thanks so
Jen. I
much.
just want to say thank you. Wonderful presentation, and thanks so much.
Excellent. And hopefully we'll see you at one of the upcoming
See you
events,
soon.
right? Yes.
Indeed. Thank you.
Really good. It'll be
Thank
good.
you.
All right. Anybody else? Anybody else? No, we're losing people. Some
Yeah,
more.
Kit, we are 20 minutes over our allotted time. So it's
Yes.
been an excellent presentation and discussion so far.
Mhm.
Thank you.
Thank you, everyone. And we will say adieu, ciao, and
Thank you. Bye-bye.
and choose.
Yes.
Be well.
Adios.
Okay.
Thank you very much.
Adios.
Thank you,
Goodbye.
everyone.
Thank you, Dr. Lawrence. Thank you, Stan.
Thank you.
Thank you.
Thank you.
Bye.
Good night, everyone. Bye.
Good night. Thank you so much for joining.
Thank you.